Hi there, welcome to Ancient Cosmos Sleep. Tonight we drift into a place where even the word edge starts to lose its meaning, where your imagination tries to draw a line around everything that exists and immediately regrets it. You picture the universe like a giant glowing room, maybe with walls, maybe with something you could bump into if you flew far enough, but the deeper you go into modern cosmology, the more that idea quietly falls apart like chalk in water. And here's the slightly uncomfortable truth: you probably won't survive this realization in any intuitive way. There is no known physical edge of the universe you could ever reach, no matter how advanced your spaceship gets or how patient your immortality becomes. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, tell me in your mind, where are you listening from, and what time is it right now in your corner of Earth? Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start by imagining the universe as something with a boundary, because your brain loves borders. Oceans have shores. Countries have lines on maps. Even your phone screen has an edge you can tap. But space itself doesn't cooperate with that habit. One of the most important mainstream historical facts in cosmology is Edwin Hubble's discovery in the 1920s that distant galaxies are moving away from us, with farther galaxies moving faster. That observation led to the idea that the universe is expanding, not exploding into empty space, but stretching itself, like the surface of an inflating balloon, except the balloon has no outside you can step into. That single insight quietly destroys the idea of a simple cosmic edge. Now your mind tries to recover by asking, okay, but surely there must be somewhere where it stops? A wall? A fade out? A final pixel? But space doesn't behave like a game map with a programmed boundary. Here's where things get weird in a very sleepy, late-night kind of way. You might hear people casually say, the edge of the universe. But what they usually mean is the edge of the observable universe. That's not a physical boundary. It's a limitation of time, not space. Light has only had about 13.8 billion years to travel since the Big Bang. So there are regions so far away that their light simply hasn't reached you yet. Not because they're blocked, but because the universe is patient and speed is strict. So you imagine standing in an endless dark ocean where your flashlight only shows a circle around you. That circle is not the end of the ocean. It's just the limit of your beam. And yes, there's a slightly funny irony here. The more powerful your telescope becomes, the more edge you discover, and the more that edge moves away from you. It's like trying to reach the horizon while walking on a treadmill that secretly speeds up. That's joke one. By the way, your cosmic treadmill is undefeated. A quirky fringe tidbit that floats around theoretical physics circles is the idea that the universe could be shaped like a 3D version of a torus, a kind of cosmic donut. In that scenario, if you travel far enough in one direction, you might eventually loop back around. No edge, just a very long return trip with terrible navigation reviews. It sounds ridiculous, but it's mathematically allowed in some models of space curvature. Meanwhile, historians still argue whether early philosophical ideas about a finite cosmos influenced how modern scientists initially resisted the concept of an expanding, boundaryless universe. The transition from everything is contained to space itself stretches was not emotionally smooth for science as a community, and now you try to picture it again. No edge, no wall, no outer ocean. Just more space, endlessly consistent, like a thought that refuses to end. But your brain still insists on framing it like geography. So you imagine flying outward, past galaxies, past clusters, past filaments of cosmic structure, until eventually, surely, something changes, except what actually happens is more subtle. The galaxies don't end. They become less observable. Their light redshifts, stretches, cools, fades into radio whispers, and then into nothing we can detect. That fading is not an edge. It's a limit of perception. Here comes your second quiet joke. The universe doesn't block you from the edge. It just slowly unsubscribes you from its updates as you get too far away. Now, the deeper conceptual shift begins. Modern cosmology suggests space itself is the thing expanding, meaning every region of space is carrying every other region apart. So if you tried to find a central point and then walk outward to find the boundary, you'd discover something unsettling. Every point looks like it's at the center of expansion. There is no privileged middle, and therefore no natural rim. This is where your intuition starts to get sleepy and confused in equal measure, because edges require something outside them. A boundary needs contrast, inside versus outside. But if the universe is all of space that exists, then outside might not even be a defined concept. It's like asking what's north of the North Pole, except stretched across everything. A quirky speculative idea, sometimes discussed in pop cosmology, is the holographic principle, which suggests the entire universe might be describable as information encoded on a distant boundary. But even in that idea, the boundary is not an edge you could travel to. It's a mathematical surface used in equations, not a cosmic fence. That distinction matters more than it sounds. Because when you keep chasing the idea of an edge, you are really chasing a feeling. The comfort that reality must end somewhere familiar. But the universe doesn't seem interested in providing that comfort. And yet, paradoxically, it also doesn't feel infinite in the way your imagination expects. Infinity should feel overwhelming, but what you actually get is structure. Galaxies, filaments, voids, patterns repeating over unimaginable scales. So you sit with this contradiction. No edge, but also no obvious end. Third joke, softly delivered like a whisper in a dark room. If the universe had customer support, the FAQ section would just say, "Edge not found. Please restart consciousness and try again." And now you begin to see why the phrase edge of the universe is less a location and more a misunderstanding. It's a linguistic leftover from thinking all things must behave like objects inside rooms. But space is not an object inside a room. It is the room, and possibly even the idea of rooms themselves. And as you settle into that thought, the concept of an edge begins to dissolve. Not because you found what lies beyond it, but because you realize the map you were using never had a border drawn in the first place. You keep drifting through that realization, like your thoughts are floating in a very quiet elevator that never quite reaches the top floor. If there is no physical edge, then what people call the edge of the universe must be something else entirely, something softer, more like a limit of sight than a wall of matter. And here's where you step directly into the concept that quietly runs modern cosmology without ever announcing itself. The observable universe horizon. This isn't a place, it's a condition. A boundary drawn not in space but in time and light. One mainstream historical fact anchors this idea. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation while troubleshooting a noisy radio antenna. That faint hiss they couldn't eliminate turned out to be the afterglow of the Big Bang itself. Suddenly, the universe had an oldest visible surface, like peeling back layers of fog and realizing there was a glowing origin to everything you can see. But even that surface isn't an edge. It's more like a fog wall made of time. So now you imagine yourself drifting outward again. Not moving through space exactly, but through errors of visibility. The farther you look, the older the universe appears, like watching a film where the remote control only lets you rewind. And here's the strange rule. You are always seeing the past. The sun you see is 8 minutes old. The nearest stars are years old. And the most distant galaxies. You're seeing them as they were billions of years ago, when Earth didn't even exist. That means distance is secretly time wearing a disguise. One quirky fringe tidbit that cosmologists sometimes play with is the idea of cosmic archaeology, and treating deep space surveys like digging through layers of historical sediment, except the sediment is light itself. Each wavelength becomes a different kind of fossil record. It sounds poetic, but it's actually close to how real observational astronomy works. And now you start to feel the subtle tension. If the universe has a visible limit, is that the same as an edge? Not quite, because what defines the observable horizon is not space stopping, but light not having enough time to reach you yet. There may be galaxies beyond that horizon right now, shining, existing, doing perfectly normal galaxy things, just permanently hidden from your current version of reality. It's like standing in the middle of a vast dark field at night, holding a lantern that only illuminates a fixed radius. Beyond that circle, the field doesn't end. It simply becomes invisible to you. First joke, drifting in gently. The universe doesn't delete what you can't see. It just refuses to forward you the email. Now you push the idea further. The observable horizon is not fixed in a simple way. As time passes, light from farther and farther regions eventually reaches you. So your cosmic view expands over time, like a slowly inflating bubble of knowledge. But here's the twist that makes everything feel slightly unreal. The expansion of the universe complicates this process. Some regions are receding from you so quickly that their light will never reach you at all, no matter how long you wait. So you end up with a paradoxical structure, a universe that becomes more visible over time, while simultaneously becoming less accessible at its farthest reaches. Historians still argue whether early interpretations of Hubble's data underestimated just how quickly cosmic expansion would reshape the idea of observational limits, or whether that understanding was inevitable once general relativity entered mainstream physics. Now your mind tries to draw a clean circle around it all. The observable universe as a sphere, with you at the center. But that image is slightly misleading, even though it's useful, because there is no true center of the observable universe. Every observer, anywhere in space, would see their own observable sphere centered on themselves. If you were on a planet in a galaxy 10 billion light-years away, you would still think you are at the center of your own visible cosmos. Second joke, very soft. The universe is extremely democratic like that. It gives everyone the same illusion of importance. And now you begin to see why the word edge keeps failing. The observable universe has a boundary, yes, but it is a boundary of perception, not existence. You imagine it again, a sphere of ancient light surrounding you, like a shell made of the oldest photons you can detect. This is the cosmic microwave background again, now understood as a kind of glowing fog at the farthest limit of your vision. It is sometimes described as a wall, but that word is misleading. It is not solid, not obstructing, not a barrier. It is simply the point where the universe becomes transparent to your instruments and then opaque to your imagination. A quirky detail that often surprises people is that this wall is not uniform. Tiny fluctuations in it, temperature variations of 1 part in 100,000, contain the seeds of all galaxies, clusters, and cosmic structures you see today. In other words, the entire complexity of the universe was once written in almost imperceptible ripples in that early light. So you are not looking at a boundary. You are looking at a blueprint, third joke, whispered like you're half asleep already. It's the only wall in existence that doubles as a construction manual for everything you know. And still, your brain tries to ask, what is beyond it? But that question starts to lose meaning. Beyond the observable horizon is not a special region. It is simply more universe that has not yet had the chance to send its story to you. The edge is not where things stop. It's where information runs out. At this point, you begin to feel something subtle shift. The universe stops behaving like a place you could potentially map completely, and starts behaving like an unfolding narrative you are always reading mid-sentence. And that realization is slightly unsettling, because it means you will never reach the final page. Not because there isn't one, but because your viewpoint is always inside the story, never outside it. As you drift with that thought, the idea of an edge starts to feel less like a location and more like a limitation of your current chapter of perception. Now you drift deeper into the real trick behind the edge you keep trying to find, and it turns out the universe has been quietly hiding it in plain sight the whole time. Light is slow enough to make reality look like a memory. That sounds almost wrong when you first hear it in your head. Light feels instant. You flip a switch, a room appears. You look up at the night sky, and everything looks present. But none of it is truly now, not a single star, not a single galaxy. Everything you see is delayed, like a cosmic broadcast arriving late because the signal has to cross unimaginable distances. A mainstream historical fact anchors this idea in reality. In 1676, the Danish astronomer Ole Rømer measured delays in the eclipses of Jupiter's moon Io, and concluded that light must travel at a finite speed. That was the first real proof that light is not instantaneous. It was a quiet revolution because it turned the universe from something immediate into something historical. And once you accept that, the edge of the universe starts to feel even stranger, because what you are really dealing with is not distance alone, but time delay layered on top of distance. You imagine yourself floating through space again, but now every step outward is also a step backward in time. The farther you look, the older the universe becomes, not metaphorically, but literally. You are not observing space. You are reading ancient versions of it. First joke slips in softly here. The universe doesn't have a refresh button, so everything you see is stuck buffering since the beginning of time. This is where the light travel time barrier becomes the hidden architecture behind everything you think you understand about. Far away. A galaxy 1 million light-years away is not just distant. It is 1 million years in the past. If something changed there right now, you would not know about it for another 1,000,000 years. And if it disappeared entirely, the version of it you currently see would still be calmly arriving, unaware. So your observable reality becomes a layered illusion. Nearby things are recent, distant things are ancient, and extremely distant things are prehistoric in a way that predates Earth itself. A quirky fringe tidbit often discussed in astrophysics circles is the idea of cosmic echoes, hypothetical delayed signals from extremely energetic events like black hole mergers, so stretched by cosmic expansion that they could arrive as faint, almost undetectable whispers spread across eons. It's not confirmed in the dramatic sense people imagine, but it reflects real thinking about how extreme distances distort signals beyond recognition. And now you start to feel the emotional twist hidden inside this physics. If everything is delayed, then the present universe is something you can never fully access. You are always looking at old news, second joke, drifting like a sleepy thought. The universe is basically the worst live stream ever. It keeps buffering, and the host died billions of years ago. You keep moving mentally outward again, trying to find where this delay becomes an edge. But there is no sudden cutoff. Instead, there is a gradual thinning of information. Light gets stretched as space expands, its wavelength lengthening, shifting from visible light into infrared, then microwave, then radio. Eventually, it becomes so stretched that it is indistinguishable from background noise. So the edge you were searching for is not a wall. It is a fade-out, and this fade-out is deeply connected to the expansion of space itself. Distant galaxies are not just sitting still waiting for their light to reach you. The space between you and them is stretching while the light travels, making the journey harder, longer, sometimes impossible. Historians still argue whether early interpretations of expanding space fully captured the philosophical shock of realizing that even emptiness itself can stretch. Carrying galaxies away faster than light can cross the gap between them. Now you begin to see why some regions of the universe are effectively unreachable, not because of distance alone, but because space expands faster than information can travel across it. These regions slip beyond your causal reach, not by moving away like objects in a sea, but by the sea itself growing between you. And yet, strangely, nothing feels like it is ending. It just becomes unreachable in principle. You imagine again, if you flew toward a distant galaxy, you would never arrive in the straightforward sense you expect. The target keeps receding, not because it is fleeing, but because the space you are traveling through is continuously stretching underneath you. Third joke, whispered like you're half asleep on a long flight. It's like trying to reach the horizon on a treadmill that's also attached to a second treadmill, and both are emotionally unavailable. A deeper realization begins to settle in. The light travel time barrier doesn't just limit what you can see, it defines what now even means in cosmology. There is no universal present moment shared across the cosmos. Now at one galaxy is not synchronized with now at another. Time itself becomes local, stitched to motion and gravity. And this is where modern physics becomes especially unsettling in a quiet way. Because if there is no shared cosmic present, then the idea of a single current universe becomes less like a fact and more like a perspective. You are always seeing slices of reality, never the whole. A quirky conceptual idea sometimes floated in theoretical discussions is look-back tomography. The idea that if you could map enough distant light sources, you could reconstruct the universe's entire history like a 3D scan built from ancient photons. It's not practical in full form, but parts of it are very real in observational cosmology. So now you are no longer standing at an edge. You are standing inside a time machine made of light, surrounded by layers of history stacked in every direction. And the further you look, the less present the universe becomes, until eventually you reach a region where light is so old, so stretched, and so delayed that it feels like the universe is dissolving into its own memory. But even then, there is no final boundary, only increasing delay, only deepening past, only a universe that refuses to let you see it all at once. You continue floating through this layered cosmos of delayed light, and by now the old picture of the universe has become difficult to hold on to. The idea of galaxies simply moving through empty space like ships crossing an ocean starts to feel incomplete, because the deeper truth is stranger. The universe is not expanding into anything. Space itself is expanding. That sentence sounds harmless at first. Then it sits quietly in your mind for a few moments and begins causing trouble. After all, every expanding thing you know expands into something. A balloon expands into the air around it. A ripple expands across water. Smoke expands into a room. Your collection of browser tabs expands into territory that concerns your computer's memory management system. But the universe appears to follow different rules. One mainstream historical fact that helped establish this picture came from the work of Albert Einstein in 1915. His theory of general relativity described gravity not as a force pulling objects through space, but as the curvature of space and time themselves. Later, when astronomers discovered that galaxies were moving apart, Einstein's equations turned out to allow an expanding universe naturally. Ironically, Einstein initially disliked that implication. He preferred a static universe and famously introduced what became known as the cosmological constant, partly to keep the cosmos from expanding. When observations later supported expansion, the story goes that he regretted the adjustment. Historians still argue whether Einstein truly called it his greatest blunder, or whether that phrase grew larger in retellings over time. Either way, the universe kept expanding whether anyone liked it or not. Now imagine a loaf of raisin bread baking in an oven. As the dough rises, every raisin sees every other raisin moving farther away. No raisin sits at the special center of expansion. The dough itself stretches. Cosmologists often use this analogy because it captures something essential. Galaxies are like the raisins. Space is like the dough. And the expansion occurs within the fabric, connecting everything. First joke arrives gently. Unfortunately, unlike the raisin bread, the universe does not come with butter. The remarkable consequence is that galaxies are not necessarily racing through space at extreme speeds. Instead, the space between galaxies is growing. This distinction matters enormously. If you throw a baseball, it moves through space. If two distant galaxies separate, because cosmic expansion stretches the space between them, something fundamentally different is happening. You begin imagining an enormous cosmic grid painted across the universe. Every square on that grid slowly grows larger. Galaxies mostly remain within their local neighborhoods, while the distances between neighborhoods increase, and because the universe is unimaginably large, even a tiny rate of expansion accumulates into astonishing separations. A quirky fringe tidbit occasionally discussed in speculative cosmology involves the possibility that space itself may emerge from quantum information networks. In some theoretical models, geometry isn't fundamental at all. Instead, space might arise from deeper informational relationships, almost as though reality is continuously generating its own stage while the play is already underway. The mathematics remains uncertain. The ideas remain controversial, but they reveal how deeply physicists have begun questioning the nature of space itself. As you drift onward, another misconception quietly falls away. People often imagine the Big Bang as an explosion occurring at one point. You picture a brilliant flash, debris flying outward, and a central location where everything started. The actual picture is stranger. The Big Bang happened everywhere, not everywhere, in the sense that an explosion spread across pre-existing space. Every location in the observable universe today emerged from the hot early universe. There is no known central point you could travel back toward. Second joke glides past. Somewhere your inner navigator is filing a formal complaint that the universe forgot to include coordinates. This absence of a center creates a fascinating consequence. If every observer sees distant galaxies moving away, then every observer can feel as though they occupy the center of expansion, yet nobody actually does. You can imagine dots drawn on an inflating balloon's surface. From any dot's perspective, all other dots move away. No dot has a privileged location. The same principle appears to describe our universe on large scales, and this leads directly to one of the most counterintuitive ideas in modern cosmology. The observable universe has a radius of roughly 46 billion light-years in every direction, even though the universe itself is only about 13.8 billion years old. At first glance, that sounds impossible. How can something appear farther away than light should have traveled? The answer is expansion. While light was traveling, space itself continued stretching. The destination moved. The journey lengthened. The cosmic ruler changed size while the measurement was being made. It is an astonishing realization. Not only are you looking into the past, the very framework containing that past has been growing throughout the entire observation. A quirky idea occasionally appearing in more speculative discussions suggests that advanced civilizations might someday detect subtle signatures of space's expansion directly within enormous engineered structures spanning interstellar distances. At present, this remains firmly in the realm of imagination. Still, it illustrates how expansion affects reality at every scale large enough to notice it. Third joke drifts in softly. The universe is basically the landlord who keeps increasing the square footage without asking anyone. You continue gazing outward. Galaxies form clusters. Clusters gather into superclusters. Superclusters connect through vast filaments. Between them lie cosmic voids so enormous that entire galactic civilizations, if they existed, might spend millions of years crossing their darkness. And through all of it, space continues stretching. Not dramatically, not explosively, just steadily, relentlessly, perpetually, like a clock whose hands move so slowly that generations pass before anyone notices. This expansion also helps explain why searching for the universe's edge becomes increasingly difficult. If space itself grows everywhere, then there is no obvious rim where growth stops. Expansion is not happening from a center outward. It is happening throughout the entire cosmic fabric. Every region participates, every distance evolves, every galaxy becomes part of a larger unfolding geometry. And as this idea settles into your thoughts, the old mental image of the universe as a giant object floating inside a larger emptiness begins fading away, because modern cosmology suggests something far stranger. The universe is not expanding into space. The universe is the space that expands. And once that realization fully arrives, the search for a physical edge starts feeling less like geography and more like a misunderstanding of what space actually is. The question shifts, not where does the universe end, but why do you expect it to end at all? And with that gentle puzzle lingering in the background of your mind, you continue drifting outward into older light and deeper horizons. The farther you drift into this expanding cosmos, the more the universe seems to transform from a place into a history book. Not a book written with ink, a book written with light. And eventually, every path through that history leads you toward one of the most extraordinary discoveries in science: the cosmic microwave background. If people casually refer to an edge of the universe, this ancient glow is often what they unknowingly have in mind, not because it is a true boundary, but because it is the oldest light you can ever hope to see. Imagine yourself moving backward through time. Galaxies become younger, stars become rarer, heavy elements become scarce. The universe grows hotter, denser, and brighter. Keep going, further back, further still, until eventually you arrive at an era when the universe resembles a blinding ocean of plasma, not stars, not planets, not galaxies. Just an immense, glowing fog of charged particles and radiation filling every direction. In that ancient epoch, light cannot travel freely. Photons constantly collide with electrons. Every attempt at movement is interrupted almost immediately. The universe is opaque. You cannot see through it. You cannot look beyond it. The cosmos resembles a dense morning fog stretching across reality itself. One mainstream historical fact marks humanity's encounter with this ancient light. In 1965, radio astronomers Arno Penzias and Robert Wilson detected a persistent microwave signal arriving from every direction in the sky. At first, they thought something was wrong with their equipment. They checked electronics. They checked interference. They even cleaned bird droppings from the antenna. The signal remained. Eventually, they realized they had discovered the afterglow of the early universe itself. First joke arrives quietly. Few scientific discoveries begin with, "Have we tried cleaning the pigeon mess off the telescope?" The signal they found was astonishingly uniform. No matter where they pointed the antenna, the glow remained. A faint whisper from a universe only about 380,000 years old. Now, 380,000 years sounds ancient from a human perspective. But cosmologically, it is practically infancy. If the universe's history were compressed into a single year, this light would emerge within the first few minutes of January 1st. Everything else, galaxies, stars, planets, dinosaurs, coffee machines, and awkward online meetings, would come much later. What happened at that moment? The universe cooled enough for electrons and atomic nuclei to combine into neutral atoms. Suddenly, photons could travel long distances without constantly scattering. Space became transparent. Light escaped. And some of those photons are still traveling today for nearly 13.8 billion years. Straight into your instruments, straight into your imagination, this ancient radiation surrounds you completely. Not above you, not below you, everywhere. You sit inside it right now. The entire Earth moves through an ocean of relic light left over from the early cosmos. A quirky fringe tidbit occasionally discussed among enthusiasts involves the strange fact that some people have jokingly called the microwave background the universe's baby picture. Surprisingly, that's not entirely inaccurate. The patterns embedded in that glow truly reveal what the young universe looked like. It is arguably the oldest photograph humanity has ever obtained, and it is not perfectly smooth. That detail matters enormously. If the early universe had been completely uniform, galaxies might never have formed. Instead, tiny temperature differences existed, variations of roughly 1 part in 100,000, tiny ripples, tiny irregularities, tiny imperfections. Yet those microscopic fluctuations eventually grew into every large-scale structure you know today. Galaxies emerged from them. Clusters emerged from them. The Milky Way emerged from them. You emerged from them. The entire visible universe traces back to minute wrinkles frozen into ancient light. Second joke drifts through gently. Apparently, the universe's greatest achievement started with what amounts to a very small formatting error. You continue staring into this glowing shell. And that's when the important realization arrives. The cosmic microwave background is often described as a wall, but it is not a wall in the ordinary sense. Nothing physically blocks your movement there. You could imagine traveling through that region if technology allowed. The limitation is observational. Before that era, light could not travel freely. The information simply cannot reach you through ordinary electromagnetic observation. It's like standing on a foggy shoreline. The fog isn't the end of the world. It's merely the limit of what your eyes can presently access. Historians still argue whether early cosmologists fully appreciated how revolutionary this discovery would become, or whether its significance only became clear after decades of increasingly precise measurements. Over time, spacecraft began mapping this ancient glow in remarkable detail. The COBE mission detected tiny fluctuations. Later, WMAP refined those measurements. Then Planck revealed an even sharper portrait of the early cosmos. Each mission transformed the microwave background from a faint hiss into a detailed cosmic map, a map of conditions billions of years before Earth existed. And yet, despite its importance, this glowing horizon is still not the edge of the universe. Beyond it lies earlier history, earlier physics, earlier stages of cosmic evolution. The microwave background simply marks the oldest light currently visible. There may be vastly more universe beyond that observational curtain. In fact, most cosmologists suspect there is. Third joke arrives softly from somewhere in the darkness. Every time you think you've found the universe's final chapter, it hands you a prequel. The deeper implication is almost poetic. When you look outward toward the microwave background, you are not seeing distant objects. You are seeing a moment, a specific event, a cosmic transition frozen across the sky. Every direction points toward the same ancient era. Every photon carries news from a universe that no longer exists in that form. And because the expansion of space has stretched these photons enormously over billions of years, what began as visible light now arrives as microwaves. The universe itself has redshifted its own baby photograph, slowing it, cooling it, aging it, yet preserving it. So as you drift within this sphere of ancient radiation, the phrase edge of the universe starts changing meaning again. Not a wall, not a border, not a cliff at the end of reality. Instead, a horizon of visibility. A place where the universe becomes opaque to ordinary sight, a glowing veil marking the oldest directly observable chapter of cosmic history. And beyond that veil, hidden behind the fog of the early plasma, waits an even deeper mystery. One that reaches back toward the first fractions of a second after the beginning itself. You linger for a while beside that ancient glow, surrounded by photons that have traveled almost the entire age of the cosmos just to arrive at your eyes, or at least at the instruments that extend your eyes far beyond anything nature originally intended. The cosmic microwave background feels so final at first, so complete, so much like a boundary. And yet the deeper you think about it, the more it begins to resemble a curtain rather than a wall. A curtain suggests something on the other side, and that brings you to one of the most fascinating ideas in modern cosmology. There may be vastly more universe beyond everything you can see, not a little more, not another nearby region hiding just out of sight, potentially an unimaginably larger expanse extending far beyond the observable horizon. You return to that flashlight analogy from earlier. Imagine standing in a dark desert at night. Your flashlight illuminates a circle around you. Everything beyond that circle remains invisible. Now suppose someone asks how large the desert is. The honest answer is simple. You don't know. The illuminated region tells you what you can see, not how much exists. The observable universe works much the same way. One mainstream historical fact supporting this perspective comes from the development of modern cosmological models during the 20th century. As observations improved, scientists increasingly realized that the observable universe is not synonymous with the entire universe. The distinction became fundamental to cosmology itself. Today, many cosmologists treat the observable universe as merely a local patch of a potentially much larger reality. And when you hear local patch, remember that this patch already contains hundreds of billions of galaxies. Cosmologists have a wonderfully understated way of describing absurdly enormous things. You imagine drifting toward the observable horizon, closer, closer still. Suppose you somehow arrive there. Would you find a sign reading "End of Universe"? Would reality fade to black? Would a cosmic security guard appear and politely redirect you? Almost certainly not, because observers located near that horizon would see themselves at the center of their own observable universe. Their horizon would extend beyond yours. Their visible cosmos would include regions forever hidden from you. First joke arrives quietly. Every observer gets their own private version of the edge, making the universe the largest personalized subscription service imaginable. This idea changes everything. The horizon is not a universal boundary. It is a personal one. A limit defined by your location and your history. Move elsewhere and the horizon changes. Wait long enough and the horizon changes. Exist at another cosmic epoch and the horizon changes. The universe itself may continue far beyond all of them. A quirky fringe tidbit occasionally discussed in speculative cosmology is the concept of super-observers, hypothetical beings capable of accessing information from regions vastly larger than our observable universe. No evidence suggests such beings exist, but the thought experiment highlights how observational limits depend on perspective rather than existence. And perspective is becoming the central character in this story, because once you separate what exists from what can be observed, the universe becomes dramatically larger, not necessarily infinite, not necessarily finite, just larger than your current view, possibly far larger, perhaps incomprehensibly larger. Some cosmological estimates suggest that if inflation occurred in the way many models predict, which you will explore more fully later, the entire universe could be many orders of magnitude larger than the observable portion. In practical terms, That means everything visible through every telescope in human history might represent only a tiny fragment of the whole. A single droplet compared to an ocean, a single page compared to a library, a single grain compared to a continent of sand. Second joke drifts past gently. Humanity spent centuries arguing about the furniture arrangement inside one room, before realizing we might be standing inside an entire cosmic shopping mall. The possibility creates a strange emotional effect. You spend your life feeling surrounded by vastness. The night sky already appears overwhelming. The Milky Way alone seems immense. The observable universe feels almost impossible to comprehend. Then cosmology casually suggests there may be far more beyond that, much more, enough more that your current notion of huge becomes a rounding error. Historians still argue whether ancient philosophical ideas about endless worlds anticipated any aspects of modern cosmological thinking, or whether the similarities are mostly superficial coincidences arising from humanity's recurring fascination with infinity. Whatever the answer, the question remains remarkably old. How much reality exists beyond what can be seen? You continue drifting outward, galaxies fill the darkness, clusters connect through filaments. Immense voids separate structures across hundreds of millions of light years. Yet none of these patterns provide evidence for a physical edge. Instead, observations suggest large-scale uniformity. The farther cosmologists look, the more the universe appears statistically similar in every direction. That uniformity becomes important. If you approached a genuine edge, you might expect asymmetry. You might expect abrupt changes. You might expect signs of a boundary. So far, observations reveal no such features. The cosmic landscape simply continues. A quirky speculative proposal known as the Island universe concept occasionally appears in discussions of very large cosmological models. In some versions, observable regions like ours are tiny islands embedded within a vastly larger structure, each separated by distances so immense that communication becomes effectively impossible. Whether such models describe reality remains unknown, but they remind you how little direct information exists beyond the horizon, and that ignorance is perfectly acceptable in science. Scientists are often comfortable saying, "We do not know." In fact, some of the best science begins there. Third joke glides through the darkness. Meanwhile, your brain remains deeply uncomfortable with that answer, and would strongly prefer a labeled map. The more you contemplate the unseen universe, the more the concept of an edge dissolves into a different question. Not where reality ends, but how much reality lies beyond observation. Those are profoundly different ideas. An edge implies termination. A horizon implies limitation. And modern cosmology increasingly points toward horizons rather than endings. You sit quietly with that distinction. Perhaps beyond the observable universe there are more galaxies, perhaps countless more. Perhaps regions so distant their light will never reach Earth. Perhaps structures larger than anything currently known. Or perhaps something even stranger. The truth is that no telescope can presently settle the matter. The horizon protects its secrets, not maliciously, not intentionally, simply because light has had only a finite amount of time to travel. And so the universe continues teaching the same lesson in different forms. The limits of your vision are not necessarily the limits of existence. Beyond the visible horizon may lie an expanse so enormous that everything you have imagined thus far occupies only a tiny corner of it. And as that possibility settles softly into your thoughts, the darkness beyond the observable universe begins to feel less like emptiness and more like unexplored territory waiting beyond the reach of light itself. And so you continue drifting beyond the horizon of visible light into a realm where observation becomes speculation and certainty begins to thin out like mist over a silent ocean. The cosmic microwave background has shown you the oldest light. The observable universe has shown you the limits of vision. But now a deeper question emerges. Why is the universe so large in the first place? Why is it so smooth? Why does space appear remarkably similar in every direction, despite regions being so far apart that according to ordinary expansion, they should never have communicated with one another? To answer that, cosmologists find themselves traveling mentally to an almost absurdly early moment, not millions of years after the beginning, not thousands, not even seconds. Fractions of a fraction of a fraction of a second, a time so early that ordinary language struggles to keep up. This is where the theory of cosmic inflation enters the story. One mainstream historical fact marks its arrival. In 1980, physicist Alan Guth proposed a revolutionary idea. The infant universe may have undergone a brief period of extraordinarily rapid expansion, growing at a rate far faster than anything occurring today, not merely expanding, explosively expanding, exponentially expanding, a tiny region of space suddenly ballooning to enormous size in an unimaginably short time. At first glance, the idea sounds outrageous. Then again, much of cosmology sounds outrageous right up until the mathematics starts agreeing with the observations. You imagine the early universe as something smaller than an atom, hotter than any star, denser than anything you can realistically picture. Then, almost instantly, space stretches, not because matter flies outward through emptiness, because space itself expands at a tremendous rate. Regions once incredibly close become separated by vast distances. Tiny quantum fluctuations become stretched into cosmic scales. Microscopic irregularities become the seeds of galaxies. The entire visible universe emerges from an unimaginably small beginning. First joke drifts by softly. The universe appears to have solved its growth problems using the most aggressive startup strategy in history. One reason inflation became popular is that it helps explain the remarkable uniformity of the cosmos. Remember that ancient microwave background from the previous section. Its temperature is nearly identical in every direction. That shouldn't happen easily. Distant regions of the universe appear too far apart to have exchanged information under ordinary expansion. Yet somehow they share almost identical properties. Inflation offers a solution. Before the rapid expansion, those regions were close enough to interact. Then inflation stretched them far apart, like drawing tiny marks on a balloon and then inflating it enormously. The marks become separated, yet they originated from neighboring locations. A quirky fringe tidbit occasionally discussed by cosmology enthusiasts involves the idea that inflation may never completely stop. In some speculative models, inflation continues eternally in distant regions of space, constantly creating new cosmic domains while local pockets, like ours, settle into calmer expansion. This concept remains highly theoretical, yet it leads to some of the most astonishing possibilities in modern science. Because if inflation is eternal, the universe could be vastly larger than anyone once imagined, perhaps effectively infinite, perhaps continuously generating new regions beyond all observation, and suddenly the notion of an edge begins looking even more fragile. Historians still argue whether inflation should be viewed primarily as a physical mechanism, a mathematical framework, or an incomplete placeholder awaiting a deeper theory beneath it. That debate remains active today. Inflation explains many observations remarkably well, yet questions remain: what caused it? Why did it start? Why did it stop where we are? No definitive answers exist. And that uncertainty gives the subject a certain dreamlike quality. You continue floating backward toward those earliest moments. The universe becomes stranger with every step. Stars disappear. Galaxies disappear. Atoms disappear. Eventually, even familiar particles begin to lose their identities. Physics enters territory where experiments become difficult and direct observation becomes nearly impossible. The early universe resembles a place known largely through clues left behind, like footprints in fresh snow after the traveler has vanished. Second joke arrives quietly. Cosmologists spend a surprising amount of time investigating events that occurred before anything was available to take notes. One of inflation's most fascinating consequences involves quantum fluctuations. At tiny scales, quantum physics allows minute variations in energy. Normally, these fluctuations remain microscopic, but during inflation, those tiny variations may have been stretched across enormous distances. The wrinkles visible in the cosmic microwave background could therefore represent quantum events magnified to cosmic size. Pause for a moment and appreciate how bizarre that sounds. The largest structures in the observable universe may ultimately trace their origins to quantum fluctuations smaller than subatomic particles. Galactic clusters, superclusters, cosmic filaments, all potentially rooted in microscopic uncertainty. The universe appears to have built its largest architecture using some of its smallest ingredients. You imagine ripples spreading across a pond. Only here the pond is reality itself, and the ripples eventually become galaxies. The scale shift feels almost impossible to grasp. Yet observations continue pointing in that direction. A quirky speculative idea occasionally appearing in inflationary discussions suggests that distant regions beyond our observable horizon could possess slightly different physical conditions, perhaps even different particle properties. Most such proposals remain highly uncertain, but they reveal how inflation naturally encourages scientists to think beyond visible boundaries. Because inflation doesn't merely enlarge the universe, it potentially enlarges the range of possibilities. Third joke glides through the darkness. Somewhere your intuition has given up and is quietly pretending all of this makes perfect sense. The deeper implication becomes increasingly difficult to ignore. If inflation stretched space enormously during the earliest moments, then the observable universe may represent only a tiny fragment of a much larger whole, perhaps an extremely tiny fragment. Everything visible through every telescope, every galaxy ever catalogued, every star ever observed, every black hole ever detected, all contained within a single local patch of a reality expanded far beyond sight. The edge you were searching for keeps retreating. First it became a horizon, then a visibility limit. Now inflation suggests that even the visible cosmos may occupy only a minute portion of existence. And the farther you follow that logic, the harder it becomes to imagine a traditional boundary waiting somewhere ahead. Instead, reality begins resembling an unfolding landscape whose true scale exceeds observation itself. You may never directly witness most of it. Light cannot bring you its stories. Time cannot bridge the gap. Yet the mathematics hints that it exists nonetheless. And as you drift through those earliest fractions of a second, watching tiny quantum ripples stretch into the architecture of galaxies, you begin to understand why cosmologists became so captivated by inflation. Because it transforms the question from "where is the edge?" into something far more mysterious. How much of reality lies forever beyond the horizon created by the universe's own explosive birth? You continue drifting outward through this inflation-shaped cosmos, carrying with you an increasingly uncomfortable suspicion. Maybe the reason nobody can find the edge of the universe is not because it is far away. Maybe it is because there isn't one. Or at least, not in the way your instincts expect. And so you arrive at one of the oldest and most persistent questions in cosmology. Is the universe infinite? It sounds simple. In practice, it may be one of the most difficult questions human beings have ever asked. After all, infinity is not merely a very large number. Infinity is not a trillion galaxies multiplied by another trillion galaxies. Infinity is something stranger, something without end, something that continues forever. And your brain, despite its many admirable qualities, did not evolve to comfortably imagine forever. One mainstream historical fact reaches back to ancient Greece, where philosophers such as Aristotle debated the nature of infinity. Aristotle accepted the idea of potential infinity, processes that could continue indefinitely, but was skeptical of actual infinities existing physically in reality. More than 2,000 years later, cosmologists are still wrestling with remarkably similar questions. Some debates take a very long time to finish. You imagine yourself standing on a perfectly flat plain, no mountains, no walls, no landmarks. You walk forward, hours pass, days pass, years pass, still no boundary. Does that prove the plain is infinite? Not necessarily. It could simply be very large. This turns out to be one of the universe's biggest problems. Even if the cosmos is finite, it may be so enormous that its curvature remains undetectable from our local viewpoint. Imagine an ant living on a gigantic sphere. The ant examines a tiny patch of surface. Everything appears flat. The ant concludes it lives on an infinite plane. Meanwhile, the sphere quietly continues, curving beyond its limited perspective. The observable universe may face a similar challenge. First joke arrives softly. The cosmos has essentially hidden its geometry. Using the same strategy as a very large parking lot, modern measurements suggest that the observable universe is extraordinarily close to flat. The data from the cosmic microwave background, galaxy surveys, and large-scale structure studies all point in that direction, but close to flat is not the same as perfectly flat. A tiny amount of curvature could exist beyond current detection limits, and that distinction matters, because different geometries imply different possibilities. A perfectly flat universe can extend infinitely. A positively curved universe could be finite yet unbounded. A negatively curved universe might possess entirely different large-scale properties. You continue imagining. Suppose space curves back on itself like the surface of Earth. If you travel far enough in one direction, you eventually return to your starting point. No edge exists. Yet the surface remains finite. You can walk forever without encountering a border. This is one of the most important conceptual shifts in cosmology. Finite does not necessarily mean bounded. A space can possess a limited volume while lacking an edge. A quirky fringe tidbit occasionally discussed among theoretical physicists involves the possibility that the universe might have a topology resembling a higher dimensional version of a torus, a cosmic donut shape. In such a scenario, light itself could potentially wrap around the universe, creating repeated images of distant structures. No convincing evidence has confirmed this idea. Yet researchers have actively searched for signatures of such topologies in the cosmic microwave background. Even extremely strange geometries remain scientifically testable. Historians still argue whether humanity's preference for imagining boundaries reflects deep cognitive habits inherited from everyday experience, or whether it reveals something more fundamental about how minds construct reality. Whatever the reason, your intuition keeps wanting an edge, a border, a final destination. Cosmology keeps refusing to provide one. Second joke drifts gently through the darkness. If the universe were designing a maze, it would absolutely remove all the exit signs. Now you explore the possibility of true infinity. An infinite universe creates remarkable consequences. For one thing, the number of galaxies becomes infinite. The number of stars becomes infinite. The number of planets becomes infinite. Potentially, even the number of observers becomes infinite. And once infinities enter physics, strange questions begin appearing. If space extends forever and matter is distributed roughly uniformly, then eventually configurations must repeat. Not nearby, not even remotely nearby, but somewhere unimaginably distant. Another Earth, another version of the Milky Way, perhaps another version of you listening to this story, not because of magic, not because of parallel dimensions, simply because finite arrangements repeated across infinite space eventually recur. This idea remains controversial and depends on specific assumptions. Yet mathematically it emerges naturally in some infinite universe models. You pause for a moment, somewhere unimaginably far away. Another you may be reaching this exact sentence. Or perhaps another version decided to become a professional cosmic raisin bread expert after Section 4. The possibilities become increasingly absurd. Third joke arrives right on schedule. Statistically speaking, infinity eventually produces someone whose life's mission is reviewing galaxies online. Of course, there is a competing possibility. The universe may be finite, not small. Not remotely small, merely limited. Large enough that the observable universe occupies only a tiny fraction of the whole. Large enough that no human civilization could ever traverse it. Large enough that its finite nature remains effectively invisible. This possibility remains fully compatible with current observations. And therein lies the challenge. The observable universe only grants access to a limited sample of reality. Trying to determine whether all space is infinite from within, that sample resembles trying to determine the size of an ocean while floating inside a single wave. You can learn a great deal, but not everything. The farther cosmologists push their measurements, the more precisely they constrain possible geometries. Yet a definitive answer remains elusive. Infinite? Finite? Curved? Flat? Wrapped? Open? Closed? The universe continues withholding its final verdict. And perhaps that is fitting, because the deeper you travel into the question of the cosmic edge, the more you discover that boundaries are not always what matter most. Sometimes the shape of reality matters more than its size. Sometimes geometry matters more than distance, and sometimes the universe reveals that an edge is not required at all. A finite universe may have none. An infinite universe certainly has none. Either possibility leaves you wandering through a cosmos that refuses to end in any familiar sense. As that realization settles quietly around you, the search for a boundary begins transforming into a search for shape itself. And shape, as it turns out, may be far stranger than size. And so your attention shifts almost naturally from size to shape. After all, if the universe might be finite without having an edge, then geometry suddenly becomes far more interesting than distance. The question is no longer merely how big reality is. The question becomes, what is reality shaped like? At first, this sounds almost silly. You are used to asking about the shape of objects. A ball has a shape, a cube has a shape, a coffee mug has a shape. Although one designed by a sleep-deprived engineer may have several competing shapes simultaneously, but the universe is not an object sitting inside another space. It is the space. So what does it even mean for space itself to possess a shape? This is where topology enters the story. Topology is one of those branches of mathematics that initially sounds intimidating and then immediately begins discussing donuts. Mathematicians are wonderfully unpredictable like that. One mainstream historical fact comes from the development of topology during the 19th century, particularly through the work of Bernhard Riemann and other pioneers who explored the geometry of curved spaces. Their ideas later became essential to Einstein's understanding of space-time and ultimately to modern cosmology. Without those mathematical tools, discussions about the shape of the universe would barely be possible. Now imagine a tiny two-dimensional creature living on the surface of a sphere. That creature cannot perceive the third dimension. To it, the spherical surface simply is reality. It can travel forever without falling off. No edge exists, yet the world remains finite. You already encountered this idea briefly in the previous section. Now you push it further, because cosmologists do not merely consider spherical universes. They consider an astonishing variety of possible topologies. Some are elegant, some are strange. Some sound like they were invented after a mathematician accidentally fell asleep on a stack of equations. First joke drifts gently past. If geometry ever hosts a costume party, topology wins every prize. One possibility is that space wraps around itself. Imagine a video game where leaving one side of the screen causes you to reappear on the opposite side, the classic arcade effect. Now imagine that happening in 3 dimensions. Travel far enough in one direction, and you return to where you started. No wall, no boundary, just a cosmic loop. A quirky fringe tidbit often discussed in popular cosmology involves the Pac-Man universe analogy. In such models, a spacecraft heading continuously in one direction could eventually circle the cosmos and return home from the opposite direction. Real versions of this idea are mathematically more complicated, but the basic intuition is surprisingly useful. Researchers have actually searched for evidence of such topologies. If light wraps around the universe, distant objects could appear multiple times in different parts of the sky. You might see the same galaxy from different directions. In an especially bizarre scenario, you might even observe ancient light emitted by your own region of space billions of years ago. No convincing evidence has been found, but the search itself demonstrates how seriously these possibilities are taken. you continue floating through these imagined geometries. Some universes resemble higher dimensional spheres. Others resemble toroidal structures. Still others possess more exotic forms that become difficult to visualize without a very patient mathematician and perhaps several whiteboards. The important realization is that topology affects what edge means, or more precisely, it affects whether edges exist at all. Most interesting cosmological models eliminate boundaries naturally. Space either extends indefinitely or folds back on itself. In both cases, the classic picture of reaching a cliff at the end of existence quietly disappears. Historians still argue whether humanity's persistent fascination with edges stems from practical experience navigating finite environments, or whether it reflects a deeper psychological desire for closure. The universe, unfortunately, appears rather uninterested in providing closure. Second joke arrives softly. Reality seems to operate under a strict no neat endings policy. As measurements improved throughout the 20th and 21st centuries, cosmologists increasingly constrained possible topologies. Observations of the cosmic microwave background became particularly important. If the universe wraps around itself at scales comparable to the observable universe, certain repeating patterns should appear in the ancient radiation. Scientists searched carefully. The results ruled out many smaller topological models, yet larger versions remain possible. The universe may still possess an unusual topology so vast that its repeating signatures lie beyond observational reach. And there it is again, that recurring theme: the horizon keeps interfering. The observable universe reveals clues, but not necessarily the whole picture. A topology larger than the observable cosmos could remain hidden indefinitely. You imagine standing inside a gigantic hall of mirrors. Most reflections lie beyond the range of your flashlight. You can infer their existence. You can build mathematical models describing them, but direct confirmation becomes difficult. A quirky speculative proposal, occasionally explored in theoretical work, suggests that subtle anomalies in cosmic background radiation might someday reveal unexpected topological features. Most candidate anomalies discovered so far have eventually faded under closer scrutiny. Yet the possibility continues motivating research, because topology matters, not only for understanding shape, but for understanding origin. Certain topologies may arise more naturally from particular early universe conditions. Some inflationary models favor certain geometries. Others permit vast families of possibility. Third joke glides through the darkness. Somewhere a cosmologist is staring lovingly at equations that resemble abstract spaghetti and calling it progress. The deeper you travel into these ideas, the more obvious it becomes that the search for the edge has transformed completely. You are no longer imagining a traveler reaching a boundary. You are examining the architecture of space itself. The universe increasingly resembles a geometric object whose global structure may never be directly visible from within. And perhaps that should not surprise you. After all, a character inside a novel cannot easily inspect the book's binding. A fish cannot easily map the entire ocean. An observer embedded within space-time faces similar limitations. You can measure local properties, you can infer large-scale patterns, you can construct increasingly precise models. But the ultimate shape of the whole may remain elusive, yet even uncertainty reveals something important. Nearly every viable cosmological model points away from a conventional edge. whether space is infinite, whether it curves gently, whether it loops back upon itself, whether it possesses some still unknown topology. The familiar image of reality ending at a physical boundary becomes increasingly difficult to maintain. Instead, the universe appears more like a continuous geometric structure, whose form extends beyond ordinary intuition. And as you drift through these mathematical landscapes, spheres without edges, loops without borders, spaces folded in ways that challenge visualization, you begin to realize something profound. Perhaps the reason nobody has ever found the edge of the universe is not because it is hidden. Perhaps it is because the geometry of reality never included one in the first place. By now, the universe has taken away quite a few comforting assumptions. The edge has dissolved into a horizon. The horizon has dissolved into a limitation of observation. The observable universe may be only a fragment of a much larger reality. Space itself may curve, wrap, or extend indefinitely. And yet one idea still remains strangely difficult to accept. The universe appears to have no center, not hidden, not distant, not waiting to be discovered, simply absent. This may be one of the most counterintuitive conclusions in all of cosmology, because whenever something expands, your intuition immediately asks, what is it expanding away from? What sits in the middle? Where did it start? These questions feel perfectly reasonable. Unfortunately, the universe seems determined to answer them with a polite but firm no. One mainstream historical fact comes from the work of Edwin Hubble during the 1920s. His observations showed that distant galaxies are generally moving away from one another, with farther galaxies receding faster. At first glance, this appears to suggest a central explosion. Yet the deeper interpretation revealed something much stranger. Every sufficiently distant observer would see the same pattern. This realization changed everything. Imagine standing on the surface of an inflating balloon, not outside it, on the surface itself. As the balloon expands, every point sees every other point moving away. No point occupies the special center of expansion. The center exists only in a higher dimensional sense outside the surface. And since our universe does not appear to be expanding into a higher dimensional space that we can observe, the analogy works only up to a point. Still, it captures something important. Every galaxy sees the universe expanding, not just us. You drift mentally into a distant galaxy billions of light years away. Suppose intelligent observers live there. They build telescopes. They measure redshifts. They analyze distant galaxies. What do they conclude? Exactly what you conclude. The universe appears centered on them. Their observable universe forms a sphere around their location. Galaxies recede in every direction. Everything looks symmetrical. First joke arrives gently. The universe has somehow convinced every observer that they're sitting in the front row seat. This creates a remarkable paradox. Everyone appears central, therefore nobody is. Modern cosmology formalizes this through what is often called the cosmological principle. On sufficiently large scales, the universe appears homogeneous and isotropic. In simpler language, it looks roughly the same everywhere and in every direction, not perfectly. Galaxies form clusters, voids exist. Structure appears at many scales, but averaged across enormous distances, no special location stands out. A quirky fringe tidbit occasionally discussed in popular science involves the so-called axis of evil, an unexpected alignment observed in certain large-scale patterns of the cosmic microwave background. Despite the dramatic nickname, most cosmologists remain cautious about interpreting it. It may represent statistical coincidence, observational effects, or something more interesting. The debate continues. Historians still argue whether humanity's instinctive search for a cosmic center reflects ancient philosophical traditions or simply the practical reality that every observer naturally experiences themselves as being at the center of their own perspective. Either way, the instinct runs deep. You feel it yourself. The idea that nowhere is special feels oddly unsettling. Humans are accustomed to maps with centers. Cities have centers. Kingdoms have capitals. Solar systems have stars. Galaxies have cores. Surely the universe should have one too. But every time cosmologists look, the evidence points elsewhere. Second joke drifts softly through the darkness. Somewhere, your inner navigator is still trying to locate the cosmic downtown district. The absence of a center has enormous implications for the edge question. Because edges and centers often come as a package. Imagine a circular pond. The center helps define the shoreline. Imagine a sphere. The center helps define the surface. But if the universe lacks a privileged center, then the very notion of a unique outer boundary becomes harder to construct. Expansion occurs everywhere, not outward from a single location. Every region participates. Every galaxy sees the same large-scale pattern. You imagine a vast grid stretching across the cosmos. Each square expands slightly. No square acts as the origin. No square acts as the destination. The entire grid evolves together. This picture aligns remarkably well with observation. And it creates a fascinating consequence. If you traveled billions of light years from Earth, you would not move closer to the universe's center. There is no center to approach. You would simply relocate within the cosmic fabric. Your observable horizon would shift. New regions would come into view. Old regions would disappear beyond the horizon. But the overall structure would remain familiar. A quirky speculative idea, sometimes appearing in philosophical discussions, asks whether a universe without a center challenges certain deeply rooted assumptions about significance and meaning. The question belongs more to philosophy than physics, yet it highlights how cosmology often influences broader ways of thinking. Because the universe's structure quietly affects how you understand your place within it, you continue drifting outward, past galaxies, past clusters, past filaments, past every familiar landmark. The expectation lingers that eventually something special must happen, a midpoint, a transition, a cosmic landmark announcing itself. Instead, the same large-scale patterns continue: expansion, structure, geometry, horizon. No center emerges. Third joke arrives like a sleepy whisper. The universe seems to have misplaced its middle and refuses to check the lost and found. This realization becomes even more striking when combined with everything you've already explored. The observable universe has a center. From your perspective, every observer possesses one. Yet the universe itself appears not to. The distinction is subtle but crucial. Your horizon is personal, the cosmos is not. What feels like the center of reality is often merely the center of your information, and that may be one of the most important lessons modern cosmology offers. The universe does not organize itself around observers. Observers organize their understanding around themselves. The difference changes everything. As this idea settles gently into your thoughts, the old image of standing at the middle of a giant expanding sphere begins fading away. In its place emerges something stranger, a universe without a preferred location, without a known center, without an obvious edge, a reality where every observer inhabits their own horizon, their own visible patch of existence, while the larger structure remains impartial and vast beyond comprehension. And once you truly accept that no center exists, the search for the edge starts feeling even more mysterious, because if there is no middle from which reality expands, where exactly would an outer boundary be measured from? The question itself begins to unravel, and in the quiet darkness between galaxies, you start to suspect that the universe may not merely lack an edge. It may be structured in a way that makes the very concept of an edge increasingly difficult to define, and so the question continues evolving. First you searched for a wall, then you searched for a horizon, then you searched for a center. Now even those ideas have begun slipping away. The universe has a peculiar habit of removing the assumptions you bring into it and replacing them with something larger, stranger, and considerably less cooperative. Which brings you to one of the most speculative possibilities in modern cosmology. What if our universe is not the entire story? What if the observable universe is merely a region within a larger universe, or more radically still, what if our entire universe is only one among many? This is where discussions of the multiverse begin, and as you might expect, things become wonderfully complicated almost immediately. A mainstream historical fact is that the modern multiverse concept grew partly out of inflationary cosmology during the late 20th century. As inflation models became more sophisticated, some versions suggested that inflation might continue indefinitely in distant regions, creating countless separate cosmic domains. What began as a technical consequence of certain equations gradually evolved into one of the most debated ideas in theoretical physics. You imagine an immense ocean, not an ocean of water, an ocean of expanding space-time. Within that ocean, bubbles form. Each bubble becomes a universe. Each expands. Each develops its own cosmic history. Each contains galaxies, stars, and perhaps observers wondering exactly the same things you are wondering now. Your universe would simply be one bubble among many. The image is often called the bubble universe scenario. And it has a strange consequence for tonight's topic. If our universe is one bubble, then perhaps it really does possess a kind of boundary, not an edge within the universe, a boundary between universes. A distinction that sounds subtle but changes everything. First joke drifts quietly through the darkness. Just when you finally stop looking for one universe's edge, cosmology introduces a whole collection of universes and asks you to start over. Of course, there is an important caution here. Unlike the expansion of space or the cosmic microwave background, the multiverse is not directly observed. No telescope has photographed neighboring universes. No spacecraft has crossed a cosmic border checkpoint. The idea emerges from theoretical models. Some physicists find those models compelling, others remain skeptical. And this disagreement is perfectly normal. Science often explores possibilities long before evidence arrives. A quirky fringe tidbit occasionally appears in discussions of multiverse theories. Some researchers have investigated whether collisions between bubble universes might leave subtle circular patterns in the cosmic microwave background. Searches have been conducted, but no widely accepted evidence has emerged so far. Still, the possibility remains fascinating. Imagine two universes brushing against one another during their earliest moments. The event would dwarf every explosion, every galaxy merger, every black hole collision, entire cosmic histories interacting, entire realities touching. The scale becomes difficult to comprehend. Historians still argue whether multiverse ideas should be viewed as legitimate scientific extensions of existing theories or as philosophical extrapolations that currently exceed observational verification. That debate remains active, and it may remain active for a very long time because the fundamental challenge is obvious. How do you test a hypothesis involving regions that may be permanently inaccessible? The question sits right at the boundary between science, philosophy, and mathematics. You continue drifting through these possibilities. Suppose countless universes exist. Would they all follow the same laws of physics? Not necessarily. Some theoretical models allow different physical constants in different regions, different particle properties, different cosmic histories, different structures. Perhaps some universes never form galaxies. Perhaps others collapse rapidly. Perhaps many remain sterile and empty. Perhaps only a small fraction produce conditions compatible with complex structures and observers. Second joke arrives softly. Somewhere out there may be a universe where cosmologists spend their evenings discussing why everything is suspiciously normal. The multiverse concept also changes how you think about the edge. In ordinary cosmology, the question is often where the universe ends. In multiverse scenarios, the question becomes whether the universe is embedded within something larger. Not space in the conventional sense, not a giant empty room, but a broader framework capable of generating multiple cosmic regions. The distinction is important, because when people casually ask, what lies outside the universe, they often imagine a surrounding void. Modern theories rarely suggest something so simple. Instead, the outside may involve structures radically different from familiar space-time, or the question itself may be poorly defined. You imagine a fish attempting to understand dry land. The fish naturally interprets everything through the language of water. Likewise, human intuition interprets reality through the language of space. Yet whatever lies beyond a universe, if anything does, may not resemble space at all. A quirky speculative proposal, sometimes discussed in theoretical circles, involves the idea that universes could emerge from black holes. In certain models, gravitational collapse might generate new expanding regions of space-time, disconnected from the parent universe. Most such ideas remain highly uncertain, but they reveal how creative cosmological thinking becomes when exploring origins and boundaries. Third joke glides gently through the cosmic darkness. The universe keeps responding to every question with 3 new questions and an additional layer of paperwork. As the possibilities unfold, a deeper realization begins taking shape. Even if a multiverse exists, your observable horizon remains unchanged. The stars overhead do not rearrange themselves. Galaxies continue their slow dance. The cosmic microwave background still surrounds you. The immediate universe remains exactly as it was. The multiverse, if real, simply extends the context. It suggests that what you call the universe may be a local chapter in a much larger story. Perhaps. Nobody knows for certain. And that uncertainty matters because science is strongest when it distinguishes clearly between evidence and speculation. The multiverse remains one of the most intriguing speculative frontiers in cosmology. neither established fact nor mere fantasy, a possibility emerging from serious theoretical work. And for tonight's journey, it serves another purpose. It reveals how dramatically the concept of an edge can evolve. An edge of the observable universe, an edge of visibility, an edge of knowledge, a boundary between cosmic domains. Or perhaps no meaningful edge at all. The farther you travel into modern cosmology, the less the universe resembles a neatly bounded object, and the more it resembles a hierarchy of horizons, nested within larger mysteries. And as you drift through those mysteries, surrounded by expanding space and ancient light, you begin approaching an even stranger frontier. Not the largest scales of existence, but the smallest. Because if the universe becomes mysterious when you look outward, it becomes equally mysterious when you look inward toward the deepest structure of space itself. And so, after wandering across billions of light years, beyond horizons, beyond galaxies, beyond even the speculative bubbles of a possible multiverse, you now reverse direction completely, not outward, inward, downward into scales so small that distance itself begins to lose its familiar meaning, because there is another place where the concept of an edge becomes surprisingly difficult to define, not at the largest scales of reality, at the smallest. You've spent much of tonight imagining space as a vast stage, a gigantic arena stretching across cosmic distances. But what if that stage is not perfectly smooth? What if deep below the scales you can directly observe, space itself becomes turbulent, granular, foamy? This is where one of the most fascinating ideas in theoretical physics appears: quantum foam. The name sounds oddly playful for something that may represent the deepest structure of reality. Yet physicists have never been afraid of whimsical terminology. After all, they gave us black holes, quarks, charm, strange particles, and cosmic inflation. Clearly nobody was enforcing a strict naming policy. One mainstream historical fact comes from the work of John Archibald Wheeler, who popularized the concept of quantum foam in the 20th century. Wheeler suggested that at unimaginably tiny scales, space-time itself might fluctuate violently due to quantum effects. To understand why, imagine zooming in, closer, closer still. You pass stars, you pass planets, you pass grains of dust, you pass atoms. Then nuclei, then subatomic particles, still deeper, still smaller. Eventually you approach a scale known as the Planck length. This is roughly 1.6 times 10 minus 35 meters, 1.6 times 10, 35, mathrm 1, 6 times 10 minus 35 milliampere distance, so tiny that ordinary intuition completely abandons the conversation. For comparison, an atom is enormous relative to the Planck length, not slightly larger, enormously larger. The difference is comparable to comparing a human being with an entire observable universe of atoms. And at these scales, physicists suspect that smooth space-time may cease behaving smoothly. Instead, geometry itself may fluctuate. Tiny distortions, tiny tunnels, tiny temporary structures appearing and disappearing almost instantly. The image often used is foam on the surface of the ocean. From far away, the water looks smooth. Close up, it becomes chaotic. First joke drifts softly by. Apparently, even space-time develops texture issues when viewed under sufficient magnification. Now, an important caution. Quantum foam remains hypothetical. Nobody has directly observed it. Current experiments cannot probe these scales. The idea emerges because quantum mechanics and general relativity, the two great pillars of modern physics, become difficult to reconcile at extremely small distances. something new appears necessary. Quantum foam represents one possibility. You imagine shrinking further. Reality becomes increasingly unstable. Distances fluctuate, durations fluctuate. Even the distinction between here and there begins to blur. At ordinary scales, space feels continuous. At Planck scales, it may resemble something more dynamic, more restless, almost alive with activity. A quirky fringe tidbit occasionally appears in speculative discussions. Some theoretical models suggest microscopic wormholes could flicker briefly into existence within quantum foam. Most physicists treat such ideas cautiously, but they illustrate how dramatically different reality may become at extreme scales. Historians still argue whether the eventual theory uniting gravity and quantum mechanics will resemble current quantum foam concepts or replace them entirely with something even stranger. That debate remains unresolved. And perhaps that uncertainty is appropriate, because every generation of physics eventually discovers that reality is more surprising than expected. You continue descending into the microscopic landscape. The remarkable thing is that the edge question reappears here in an unexpected form. At large scales, you asked whether the universe has an outer boundary. At tiny scales, physicists ask whether space itself has a smallest possible unit, a minimum distance, a fundamental limit, an edge beneath which the concept of location ceases to exist. Some theories suggest yes. Others suggest no. Some versions of quantum gravity imply that space-time may be discrete rather than continuous. Others preserve continuity while modifying geometry in subtler ways. Second joke arrives gently. Physicists have spent decades arguing about whether reality uses pixels. The challenge is formidable. General relativity describes space-time as smooth and continuous. Quantum mechanics describes nature through probabilities and fluctuations. Both theories work extraordinarily well, yet combining them remains one of the greatest unsolved problems in science. Black holes intensify the mystery. Near their centers, known physics begins breaking down. Densities become extreme. Curvature becomes extreme. The mathematical descriptions stop behaving sensibly. Many researchers suspect that quantum gravity, and perhaps quantum foam, plays a crucial role there. You picture space-time not as an empty container, but as an active participant, a dynamic structure, a physical entity capable of evolving, fluctuating, and perhaps emerging from even deeper processes. This perspective transforms the way you think about the universe. Space is no longer merely where things happen. Space becomes one of the things happening. A quirky speculative proposal sometimes explored in cutting-edge research suggests that space-time itself may emerge from quantum entanglement. In these models, geometry arises from informational relationships rather than existing fundamentally on its own. Whether such ideas prove correct remains unknown, yet they point toward a profound possibility. Perhaps space is not the foundation of reality. Perhaps it is a consequence of something deeper. Third joke drifts through the darkness. Just when you finally learn how space works, physics quietly informs you that space might not be fundamental after all. As the smallest scales unfold before you, the search for the edge changes once again. You are no longer asking where the universe ends. You are asking what the universe is made of, what space-time is, whether distance itself possesses a limit, whether geometry has an underlying structure, whether reality contains a deepest layer, and every answer seems to open another question The observable universe gave you horizons. Inflation gave you vastness. Topology gave you shape. The multiverse gave you possibilities beyond familiar boundaries. Now quantum foam gives you a new mystery entirely. Perhaps the ultimate edge is not far away. Perhaps it lies hidden beneath every point in space, buried within scales so tiny that ordinary concepts collapse. And as you continue descending toward those unimaginable depths, reality begins to feel less like a finished construction and more like an unfinished conversation between geometry, quantum mechanics, and time itself. A conversation whose final words have not yet been spoken. You continue drifting through those microscopic depths, where space-time itself begins to look uncertain, and where every answer seems to dissolve into a deeper question. At this point in the journey, something curious has happened. The universe has not revealed its edge. Instead, it has revealed the limits of your explanations. And those limits may be the closest thing physics currently possesses to a boundary, not a boundary in space, not a wall at the end of existence. A boundary in understanding, because eventually every successful scientific theory reaches a place where it can go no farther, a place where its equations stop making reliable predictions, a place where nature quietly says, "You need a better map." One mainstream historical fact illustrates this beautifully. In 1915, Albert Einstein introduced general relativity, one of the most successful scientific theories ever created. More than a century later, it continues to describe gravity with astonishing accuracy, predicting everything from black holes to gravitational waves. Yet even Einstein's masterpiece has limits. Pivot far enough, compress enough matter into a small enough volume, approach conditions close enough to the Big Bang, and the equations begin producing infinities. That is usually a warning sign in physics. Nature rarely hands out infinities as final answers. More often, infinities indicate that a theory has wandered beyond the region where it can be trusted. Imagine using a road map to navigate a city. The map works beautifully, until you try using it to understand the molecular structure of asphalt. At that point, the problem isn't reality, the problem is the map. First joke drifts gently through the darkness. Physicists have spent generations discovering that reality keeps extending beyond the user manual. This realization becomes especially important near the earliest moments of cosmic history. As you travel backward toward the Big Bang, temperatures rise, densities increase, energy levels climb. Eventually you reach conditions so extreme that the known laws of physics can no longer be confidently applied. The mathematics enters territory where certainty fades. This is not because scientists are careless. It is because the universe becomes extraordinarily difficult. You imagine standing before a fog-covered mountain range. The nearby slopes are clear. The distant peaks vanish into mist. You can see where the terrain appears to continue. You can build models. You can make educated guesses. But direct visibility ends. Modern cosmology faces a similar challenge when approaching the earliest fractions of a second after the Big Bang. A quirky fringe tidbit occasionally discussed among theorists involves pre-Big Bang models that attempt to describe conditions before the universe's hot early phase. Some involve cosmic bounces. Others involve cyclic universes. Others propose entirely different frameworks. None currently enjoy decisive observational support. Yet the very existence of these ideas reveals something important. Physicists are actively trying to push beyond the boundaries of current understanding. Historians still argue whether future breakthroughs will emerge from refining existing theories or from a conceptual revolution as dramatic as relativity itself. Nobody knows. Scientific revolutions are notoriously difficult to schedule. You continue moving through these limits. Black holes provide another fascinating example. General relativity predicts that matter collapsing under sufficient gravity can form a singularity, a region where density becomes effectively infinite. But most physicists suspect that the true story is more subtle. Quantum effects likely intervene. A deeper theory likely takes over. The singularity may represent not a physical object, but a signal that existing mathematics has reached its domain of failure. Second joke arrives softly. Singularities are physics equivalent of a computer displaying something has gone very wrong. The same challenge appears when discussing the beginning of the universe. Popular descriptions often present the Big Bang as a singular starting point, a moment when everything emerged from nothing, a definitive beginning. Yet many physicists view that picture cautiously. The singularity itself may not be a physical event. It may simply mark the edge of current theories. Beyond that edge, new physics awaits. And this brings you back to tonight's central theme. The universe keeps replacing physical boundaries with conceptual ones. You search for an edge in space. You find a horizon. You search beyond the horizon. You find inflation. You search beyond inflation. You encounter topology. You search beyond topology. You reach quantum gravity. You search beyond quantum gravity. And eventually you arrive at the limits of knowledge itself. A quirky speculative proposal known as loop quantum gravity suggests that space-time may possess a discrete structure at extremely small scales, potentially eliminating certain singularities altogether. Another major approach, string theory, proposes that fundamental entities are tiny vibrating structures rather than point particles. Neither framework has yet achieved decisive experimental confirmation. Yet both represent serious attempts to extend the map, and extending the map is one of science's favorite activities. Third joke drifts through the cosmic silence. Every time physicists discover a boundary, they immediately begin looking for a ladder. The remarkable thing is that these limits are not failures. They are opportunities. Every major breakthrough in physics emerged from recognizing where previous theories stopped working. Newtonian mechanics worked brilliantly. Then relativity expanded the picture. Classical physics worked brilliantly. Then quantum mechanics expanded the picture. Today's theories work brilliantly. Perhaps something even deeper awaits. You imagine future scientists looking back on current cosmology the way modern physicists look back on 19th century science, not as wrong, but as incomplete. Part of a larger story, a stepping stone toward a more comprehensive understanding. And perhaps that future theory will finally reveal whether space-time has a smallest scale, whether inflation truly occurred, whether multiple universes exist, whether the Big Bang had a precursor, whether reality possesses a deeper architecture beneath geometry itself, or perhaps it will reveal mysteries nobody has yet imagined. The history of science suggests the latter is highly likely, because reality repeatedly demonstrates an astonishing talent for surprising observers. As you sit quietly with that thought, the universe begins to feel less like a puzzle waiting to be solved, and more like a horizon that continually recedes as understanding grows. The edge, if one exists, keeps moving, not because reality changes, because knowledge expands. And in that sense, the frontier of cosmology may not be located somewhere among the galaxies. It may reside wherever curiosity encounters the limits of explanation, a boundary that every generation reaches and every generation attempts to cross, and so you arrive at perhaps the strangest question of the entire journey. Not where the edge is, not how large the universe might be, not whether space curves, loops, stretches, or multiplies into countless cosmic domains. A simpler question, a more dangerous question. What does outside the universe even mean? At first glance, the question feels perfectly reasonable. If something has an inside, surely it must have an outside. If something exists, surely it exists somewhere. Your everyday experience encourages exactly this way of thinking. A house exists within a neighborhood, a city exists within a country, a planet exists within a solar system. Everything appears nested inside something larger. So naturally, your mind tries to place the universe into the same pattern. The universe must be inside something, right? Yet the deeper you travel into cosmology, the more that assumption begins to wobble. One mainstream historical fact comes from the influence of general relativity during the 20th century. Einstein's framework fundamentally changed the way scientists think about space and time. Instead of treating space as a passive stage where events occur, relativity describes space-time itself as part of the physical universe. That shift matters enormously, because once space becomes part of reality rather than the container of reality, asking what lies outside space becomes far less straightforward. Imagine a character living entirely on the surface of a sphere. Every direction available to that character lies along the surface. The question, what is beyond the edge, makes little sense because there is no edge. Likewise, modern cosmology increasingly suggests that the universe may not possess an external spatial boundary in the ordinary sense, and if no boundary exists, the notion of an outside becomes difficult to define. First joke drifts softly through the darkness. The universe has apparently responded to the question, what's outside, by questioning the definition of outside. You continue contemplating this. The word outside assumes a larger space surrounding the thing in question, but if the universe includes all physical space, then there may be no larger spatial arena available, not hidden, not distant, simply absent. This is one reason cosmologists often become cautious when discussing what lies beyond the universe. The language itself may be misleading. Human intuition evolved inside a small environment filled with objects. It naturally assumes containers within containers. Reality at cosmic scales may not cooperate. A quirky fringe tidbit occasionally appears in philosophical cosmology. Some thinkers have proposed that the question of what lies outside the universe resembles asking what is north of the North Pole. The question appears meaningful grammatically, but may lack a meaningful answer physically. Whether that analogy is perfect remains debated, yet it captures something important. Certain questions may depend on assumptions that fail at cosmic scales. Historians still argue whether ancient philosophical discussions about the nature of existence anticipated aspects of modern cosmological thinking, or whether the similarities merely reflect humanity's recurring fascination with ultimate questions. Either way, the question itself is ancient. What contains reality? You imagine standing at the edge of a map. Ancient maps sometimes showed unexplored regions labeled with warnings. Beyond here be dragons. Beyond here be monsters. Beyond here be uncertainty. Modern cosmology is more restrained. Usually, but when discussing what lies beyond space-time itself, uncertainty remains very real. Some theories suggest the universe may be self-contained. Others allow larger frameworks. Still others imply that the question itself becomes meaningless at fundamental levels. Second joke arrives quietly. After centuries of investigation, one of science's official answers remains: the question may require maintenance. You drift deeper into the conceptual challenge. Suppose someone asks where the universe was before the Big Bang. Again, the question feels natural. Everything in your experience happens after something else. Every event possesses a prior event. Every story begins after another story. Yet many cosmological models suggest that time itself emerged alongside the early universe. If time began with the Big Bang, or with whatever process ultimately produced our cosmic history, then asking what happened before may resemble asking what lies north of the North Pole. The framework required by the question may not exist. This does not necessarily mean the universe emerged from absolute nothingness. That phrase often creates confusion. It simply means that familiar concepts, such as before, after, inside, and outside, may lose their ordinary meanings under extreme conditions. A quirky speculative proposal occasionally explored in quantum cosmology suggests that space-time may emerge from more fundamental mathematical or informational structures. In such frameworks, space itself is not primary. Instead, geometry arises from deeper relationships. If such ideas prove correct, then asking what exists outside space might resemble asking what exists outside a coordinate system. The question changes entirely. Third joke drifts gently through the silence. Somewhere, your intuition has requested a refund and a simpler universe. Yet despite all this complexity, an important lesson begins to emerge. The universe repeatedly challenges assumptions imported from everyday experience. Edges work well for rooms, not necessarily for space-time. Outsides work well for boxes, not necessarily for reality itself. Centers work well for circles, not necessarily for cosmic expansion. The deeper you travel into cosmology, the more language becomes part of the puzzle. Words carry hidden assumptions. Questions carry hidden structures. And sometimes the hardest part of understanding the universe is discovering which assumptions need to be abandoned. You continue floating through the darkness. Galaxies shimmer far away. Ancient microwave photons drift across space. Expansion quietly stretches the cosmic fabric. And throughout all of it, the universe remains under no obligation to fit human intuition. Perhaps there is something beyond our universe. Perhaps there is not. Perhaps the question will eventually acquire a precise scientific answer. Perhaps it will transform into a different question altogether. For now, uncertainty remains. But uncertainty is not emptiness. It is possibility. It is the space where new ideas emerge. The frontier where knowledge has not yet settled. And as you sit with that uncertainty, the idea of an outside begins to soften. Not because you have discovered what lies there, but because you have learned that the meaning of there may itself be part of the mystery. And in that realization, you find yourself approaching the final horizon of tonight's journey. Not a physical edge, not a cosmic wall, but something much closer to home, the ultimate limit that shapes every attempt to understand the universe, the boundary between reality itself and what any observer can ever know about it. You have traveled a very long way tonight, across expanding galaxies, past horizons made of light, through the afterglow of the early universe, beyond the possibilities of inflation, across strange topologies and speculative multiverses, down into quantum foam, up against the limits of physical law. And through all of it, one thing has happened again and again. Every time you thought you were approaching the edge of the universe, the edge transformed into something else, a horizon, a limitation, a deeper question, a larger mystery. Now you arrive at the final conceptual horizon of the journey, not the edge of the universe, the edge of observation itself. Because the deeper truth hidden beneath everything you have explored is remarkably simple. The universe and your knowledge of the universe are not the same thing. That distinction may be the most important lesson in all of cosmology. One mainstream historical fact illustrates this beautifully. Throughout history, every major expansion of human knowledge has pushed perceived boundaries outward. From the realization that Earth is not the center of the cosmos to the discovery of galaxies beyond the Milky Way, every generation has watched its apparent horizon retreat as new observations became possible. The edge kept moving, not because reality changed, because understanding expanded. You could imagine ancient observers standing beneath the stars. To them, the visible sky was nearly the entire universe. The stars appeared fixed. The cosmos seemed relatively small. Then telescopes arrived. The horizon moved, galaxies appeared. The universe became larger. Then radio astronomy arrived. The horizon moved again. Then space telescopes. Agon, agon, agon. Every improvement in observation transformed what humanity considered the limits of existence. First joke drifts softly through the darkness. The universe has spent centuries proving that every cosmic fence humans build is actually just a temporary construction project. And perhaps that pattern will continue. Future civilizations may observe phenomena invisible today. Future instruments may reveal structures currently hidden. Future theories may connect ideas that now appear unrelated. The map will continue growing, yet a subtle challenge remains. No matter how advanced observation becomes, every observer exists within reality. You cannot step completely outside the universe to inspect it from the exterior. You remain embedded within the thing you are trying to understand, like a character attempting to read the entire novel from inside the story, like a fish attempting to survey the whole ocean while still swimming through it. Observation itself possesses limits. A quirky fringe tidbit occasionally discussed in philosophy of science involves the notion that certain aspects of reality may remain permanently inaccessible. Not because of technological shortcomings, but because of fundamental observational constraints built into the structure of the universe itself. Whether such limits exist remains uncertain, but the possibility is taken seriously. Historians still argue whether the history of science demonstrates the eventual conquest of every barrier or whether some horizons are genuinely permanent. The answer remains unknown. You continue drifting through that uncertainty. And surprisingly, it feels peaceful, because uncertainty is often portrayed as failure. Yet science treats uncertainty differently. Uncertainty marks the frontier, the place where discovery becomes possible, the place where questions remain alive. Second joke arrives gently. Scientists are among the few people who can become genuinely excited after discovering they have no idea what's going on. Now think back to the original question. What exactly is what we call the edge of the universe? After everything you have explored, the answer feels very different. The observable universe possesses a horizon. But that horizon is not a wall. The cosmic microwave background forms a boundary of visible light. But it is not an edge. Inflation suggests vast regions beyond observation. Topology allows finite spaces without borders. The absence of a center undermines familiar notions of outer limits. The multiverse, if it exists, extends the question further. Quantum gravity reveals possible limits beneath space-time itself. And throughout all of it, physical boundaries repeatedly dissolve into informational boundaries. The edge keeps becoming a limit of knowledge rather than a limit of existence. That realization is both humbling and beautiful, because it means the universe is not simply something you inhabit, it is something you continuously discover. Every observation adds another piece. Every theory adds another perspective. Every unanswered question points toward another horizon. Third joke drifts through the quiet cosmos one last time. The universe may be the only thing that becomes larger every time you learn more about it. And now, as the journey begins slowing toward rest, you notice something comforting. The absence of an edge does not make reality less meaningful. If anything, it makes it more wondrous. A finite wall would provide closure. A horizon provides possibility. A boundary says stop. A mystery says continue. And perhaps that is why the universe has fascinated observers for so many thousands of years. Not because it offers final answers, because it continually invites deeper questions. You sit quietly beneath a sky filled with ancient light. Stars shine across distances so vast that language struggles to describe them. Galaxies drift through expanding space. Invisible horizons surround every observer, and beyond every horizon waits another layer of reality still hidden from view. The universe remains unfinished in your understanding, and perhaps always will. Yet that incompleteness is not a flaw. It is part of the experience, part of the invitation, part of the wonder. As the final moments of the journey settle around you, allow the pace of your thoughts to slow. Let the galaxies drift farther apart. Let the horizons soften. Let the questions become quieter. You no longer need to search for an edge. You no longer need to imagine walls at the end of existence or borders painted across the cosmos. Instead, picture yourself floating peacefully in a vast ocean of stars, not moving, not searching, simply resting. Around you, ancient photons continue their endless journeys through space. The faint afterglow of the early universe still whispers across the darkness. Galaxies continue expanding away from one another with patient cosmic grace. And somewhere beyond every visible horizon, reality continues unfolding exactly as it always has. There is something calming in that thought. The universe does not require you to solve it tonight. It does not demand final answers. It does not expect complete understanding. It simply exists vast et quet, ancient and beautiful. The mysteries remain. The horizons remain. The unanswered questions remain. Yet for this moment, none of them needs solving. You can let them drift gently into the distance, like starlight fading across a calm sea. The edge of the universe, if there is one, can wait. Tomorrow's astronomers can keep searching. Tomorrow's physicists can keep calculating. Tomorrow's dreamers can keep wondering. Tonight, you can simply rest beneath the immense canopy of existence and allow yourself to become part of its stillness. The stars grow softer, the darkness grows warmer, the questions grow quieter. and the universe continues its patient unfolding beyond every horizon, beyond every theory, beyond every edge you once imagined.